Proxima Centauri, the nearest star to our planetary system, has for quite a long time been a subject of interest for space experts. This little red dwarf, found in 1915 by Scottish space expert Robert Innes, is part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its proximity just 4.24 light-years away, it remains intangible to the eye because of its low brilliance. However, Proxima Centauri holds colossal scientific value, particularly as the host star of Proxima b, an exoplanet that orbits within the star's habitable zone. Red dwarf stars like Proxima Centauri are smaller, cooler, and much longer-lived than stars like our Sun. Their low brightness makes them challenging to observe, but it also means their habitable zones are much closer to the star. For Proxima Centauri, this means an orbital distance of around 0.05 astronomical units, only a small fraction of the distance between Earth and the Sun. This proximity exposes Proxima b to intense stellar activity, including frequent solar flares and elevated levels of radiation, making its environment very different from Earth's. The discovery of Proxima b was a significant achievement in exoplanet research. Using the radial velocity method, space scientists identified subtle wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These wobbles allowed researchers to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory formally confirmed the existence of Proxima b, marking a breakthrough in the search for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights into Proxima b, they come with significant limitations such as atmospheric distortion and light interference, which hinder the ability of Earth-based telescopes to capture detailed information about the planet surface or atmosphere. Most of the data we have, such as its mass, distance from the star, and orbital characteristics, comes from indirect measurements. To uncover further insights into Proxima b's atmosphere and its potential for life, advanced observational tools like the James Webb Space Telescope JWST are essential. Proxima Centauri and Proxima b's role as a gateway to understanding exoplanetary systems cannot be overstated. As the closest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima b in particular presents a captivating possibility: a rocky, Earth-sized planet with the potential to hold liquid water and possibly life. However, the challenges posed by its harsh environment make it a complex puzzle for scientists to solve. The James Webb Space Telescope JWST is not just another tool in the arsenal of space science. It is a revolutionary instrument designed as the successor to the Hubble Space Telescope. JWST was built to overcome the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided crucial insights into the universe, including the age of the cosmos and the discovery of thousands of galaxies, its capabilities are limited by its focus on visible and ultraviolet light. JWST, on the other hand, is designed to observe the universe in infrared wavelengths, allowing it to peer through vast clouds and uncover features hidden from Hubble. One of JWST's key design features is its primary mirror, which spans a stunning 6.5 m in diameter. more than twice the size of Hubble's mirror. This larger mirror enables JWST to gather much more light, allowing it to observe even the faintest and most distant objects. The mirror is coated with a thin layer of gold to enhance its infrared reflectivity and is made up of 18 hexagonal segments that work together to form an exceptionally sensitive observational platform. Another remarkable innovation is JWST 5-layer sun shield, which keeps the telescope's instruments at a stable temperature of about 233 degrees Celsius. This ultra-cold environment is essential for detecting faint infrared signals without interference from the telescope's own heat. Each layer of the sun shield is made from a special material called Captain, coated with aluminum to reflect sunlight. Unlike Hubble, which orbits Earth, JWST operates from the second range point L2, a stable position about 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. JWST can focus on everything from the earliest galaxies to the atmospheres of exoplanets like Proxima b. Its ability to detect infrared light is particularly critical, as it enables scientists to study red-shifted objects, those whose light has been stretched to longer wavelengths. As the universe expands, JWST capabilities extend far beyond mere observation. It is designed to answer some of the most fundamental questions in science, such as the origins of galaxies, the formation of stars, and the conditions that could support life on other planets. With its advanced instruments, including the near-infrared camera NCAM, the mid-infrared instrument MIRI, and the near-infrared spectrograph NSPEAK, JWST is not just a telescope, it is a time machine, a research laboratory, and a symbol of human creativity. Proxima b has captivated both scientists and the public as a potential second Earth. Located within its star's habitable zone, the planet has the right conditions to support liquid water, an essential ingredient for life as we know it. With a mass about 1.17 times that of Earth, Proxima b is likely a rocky planet, similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima b is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in eternal daylight while the other is in perpetual darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, could offer a narrow habitable zone with conditions mild enough to support life. The challenges presented by Proxima b's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can release bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harsh of space. If Proxima b retains any atmosphere, it likely requires a strong magnetic field to protect it from radiation. Without such protection, the surface environment would be hostile to life as we know it. Despite these challenges, scientists remain hopeful about the potential for life on Proxima b. The planet's location within the habitable zone suggests that liquid water could exist either on its surface or in subsurface reservoirs life might adapt to the harsh conditions in a similar way that Earth organisms thrive. In extreme environments such as deep sea, hydrothermal vents, or high radiation zones, these adaptations could include radiation-resistant subsurface habitats, or novel biochemical cycles. The search for life on Proxima b is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions: are we alone in the universe? Proxima b presents an intriguing possibility, a rocky Earth-like world that could harbor the conditions necessary for life. As our technology advances, so does our ability to explore this captivating planet and uncover its secrets. While Proxima b holds tempting possibilities, its environment is heavily influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf, smaller, cooler, and much less luminous. Its reduced size and temperature mean that its habitable zone is much closer, pulling a Proxima b into an orbit just 0.05 astronomical units from the star, nearly 20 times closer than Earth is to the Sun. This proximity creates a unique set of challenges for the planet and any potential life it might harbor. One major issue is Proxima Centauri's stellar activity, especially its intense and frequent solar flares. These flares are sudden, powerful bursts of energy that release high doses of X-rays and ultraviolet radiation. Such events are much more common and severe in red dwarfs than in stars like our Sun. For Proxima b, this means a constant bombardment of high-energy particles that could strip away the planet's atmosphere over time. Without a protective magnetic field like Earth's, any atmosphere on Proxima b would be vulnerable to erosion, leaving the surface exposed to harsh radiation. Even if Proxima b retains some of its atmosphere, the radiation from Proxima Centauri presents significant challenges to life. High levels of ultraviolet radiation can break chemical bonds, preventing the formation of complex organic molecules. This would severely limit the potential for life to develop or sustain itself on the planet's surface. On Earth, organisms like Deinococcus radiodurans have evolved mechanisms to repair DNA damage caused by radiation, suggesting that life on Proxima b might also adapt. However, the level of radiation resistance required could be extreme, possibly requiring entirely new biochemistries. Interestingly, Proxima b's tidally locked nature might offer some protection. While one side of the planet faces constant radiation from Proxima Centauri, the dark side could act as a refuge. Subsurface habitats or deep caves might shield potential life forms from the worst of the radiation. Moreover, if Proxima b has subsurface oceans, they could provide a stable radiation-free environment where microbial life could flourish, much like the ecosystems around hydrotherm vents on Earth. Despite these difficulties, scientists remain optimistic that Proxima b's extreme environment offers an exciting opportunity to study life's resilience by observing how organisms might survive or even thrive under such conditions. Researchers can expand their understanding of what makes a planet habitable. Proxima b is not only a potential home for life but also a laboratory in the search for life's adaptability across the universe. The possibility of life on Proxima b raises more questions than it answers, but it also offers a new perspective on the Definition of habitability. The search for life on Proxima b is not just a scientific mission but a philosophical one. It challenges our understanding of what constitutes a habitable environment and broadens our search for life to include planets with extreme conditions, Proxima b's harsh radiation environment, and tile locking. Force scientists to reconsider the traditional notion of habitability, which has generally been based on Earth-like conditions. One of the key aspects of studying Proxima b is its potential to uncover new insights into how life could adapt to extreme conditions. If life can indeed survive and evolve in such an inhospitable environment, it could redefine our expectations for where life might exist in the universe. Understanding these possibilities could help scientists focus their search on other exoplanets that share similar traits to Proxima b, expanding the criteria used to identify potentially habitable worlds. The study of Proxima b also fits into the broader context of the search for exoplanets, planets that exist outside our solar system. In recent decades, the discovery of exoplanets has exploded, with thousands of these distant worlds now known. The study of these planets, especially those in their stars' habitable zones, has shifted our perspective on the possibility of finding life elsewhere. Proxima b, with its proximity and potential for liquid water, is one of the most intriguing candidates. However, it is far from unique. As technology advances, the number of known potentially habitable exoplanets continues to grow. In addition to studying Proxima b, astronomers are focusing on planets around other stars, particularly those that share characteristics with our Sun. These Sun-like stars offer habitable zones that might be more stable and conducive to life. However, Proxima b orbiting a red dwarf star presents a contrasting case that challenges conventional thinking about habitability. Its study can provide valuable lessons on the resilience of life and how it might exist in more extreme conditions. Proxima Centauri, the star that hosts Proxima b, also offers scientists a fascinating opportunity to better understand stellar behavior, particularly the differences between stars like our Sun and red dwarfs. Red dwarfs are much more common in the universe than Sun-like stars, and studying these stars can help us understand how different types of stars influence the potential for life on surrounding planets. Proxima Centauri's frequent stellar flares and their effects on Proxima b's atmosphere may help researchers figure out how various types of stellar activity impact planetary conditions, providing critical clues for the search for life elsewhere. For now, Proxima b remains a mystery. However, technological advances and future space missions may eventually provide the data needed to answer one of the most important questions humanity faces: is there life beyond Earth? With each new discovery, the possibility of finding life on Proxima b or other exoplanets becomes more plausible, and the implications of such a finding would be profound.